Hello, a very good evening to one and all present here. Welcome to the 11th and the penultimate weekly live session for the NPTEL course on remote sensing principles and applications. This course is brought to you by NPTEL and the SWAM initiative. I am Abhishek Chakraborty, a PhD student under the Prime Minister's Research Fellowship Scheme from the Interdisciplinary Center for Water Research, IISc at IISc Bangalore. And this course is being tutored by Professor Ishwar Rajshekharan from the Department of Civil Engineering at IIT Bombay. First things first, the general information. First of all, the video recordings of all the sessions will be made available on the YouTube channel. I've already shared you the link of that channel. The files relevant to the sessions will be made available through a Google Drive folder. So far, I've already uploaded everything till the 10th and the last weekly live session. The files and the video recordings will be made immediately available after the class. I try to do it almost within an hour after the class ends. And last but not the least, if I have chosen to show any image in this presentation, and if they are from internet, we don't intend to plagiarize it. They are solely for education purpose. So far I've already uploaded the video recordings of the previous 10 weekly live sessions. Uh, and this is going to be the penultimate one, and this link which you see is the one for the Google spreadsheet containing the YouTube video links for each of the weekly live session, as well as the illustrations which I actually showed during the course of this 2-hour session. Today we are almost towards the end of this course, so we will be discussing a few questions relevant to the 12th assignment, and I intend to keep the last weekly live session, that is the 12th weekly live session, solely for revising of the concepts, uh, uh, which will focus on your preparation for the examination. So let's again take a set of 10 questions for the day, try to solve them and move ahead with them. Okay, so the first question is the classification technique that classifies objects into different classes within a pixel is: A. Supervised classification, B. Unsupervised classification, C. Subpixel classification, D. Per pixel classification. So the basic and the most important word here is within a pixel. Within a pixel, so it has to be within, so it has to be C, the subpixel classification. Sub means within that, so that is okay, but let me just show you what are these things exactly. So subpixel classification, subpixel classification, it allows the identification of multiple land cover types within a single pixel, and it is also called as a fractional classification, also called fractional classification. So what's the meaning of it? Let's just assume that it is a raster, and a raster constitutes of several pixels. You know that already. Okay, so let these be the pixels. So let's just extract this pixel for our interest. So this pixel, according to subpixel classification, will give an idea that around 30% of it is let us see C3 grass, 30% is C4 grass, 40% is forest. So I'm just giving an example. Uh, so within a pixel also, it will give you the fractional coverage of the land classes which you are considering, and that is what we call as the subpixel classification. Now, what do we actually do here? Let me take another one. Subpixel classification. So each pixel treated as mixture of several land cover types. So we give that proportion basically, mixture of several land cover types within a single pixel. Okay, so this is the by a proportion of each land cover type, and it is represented as a fraction. Represented as a fraction or percentage. So percentages are also nothing but fractions itself. This is the one which I showed here. So these are nothing but fractions. Okay, so that is what is subpixel classification. What about per pixel classification? So per pixel classification is the representation of the dominant land cover class. Sorry for this. Just a second, please. Hello. Hello, good evening, sir. Sir, may I call you at around 8 o'clock? I'm actually having this NPTEL session for my TA requirements. Yes, sir. Actually, I'm the TA in it. Okay, so I will call you around 8 o'clock. Then. The second one is the per pixel classification. Uh, Per pixel classification is that each pixel is assigned a single class label based on the predominant land cover type within a pixel. Okay, so this is the thing. Let me again show it using that same example. Let it be a raster. Let's think about this pixel. So if this pixel has, let us say, 30 percentage C3 grasses proportion, 30 percentage C4 grass proportion, and 40 percentage forest. So the dominant land cover type is forest. Okay, so the land cover class assigned to such a pixel under a per pixel classification would be the forested land cover type. Okay, so let's again talk a bit about the subpixel classification. Subpixel classification So it is about analyzing spectral signature of each pixel and identifying the land cover proportion. Okay, so what may be the techniques to find it out? The techniques may be linear spectral mixing or something known as fuzzy classification or the Bayesian methods. It's a statistical method actually. Okay, so what do we do in linear spectral mixing? Okay, so we find out. I mean, if the spectral resolution of the sensor is fine enough, we may know what is the reflectance pattern basically. Whether it is say like this, the one for vegetation, or like this, the one for water. So for each, I mean, you will get a mixture of signals basically. The spectral resolution may be, I mean, this kind of signal with respect to the wavelength will be very different. So you need to decompose it into individual components for each depending on each land cover type, and that is how you get to know the proportion of each land cover type within that particular pixel. So it's very complex, and there are methods like linear spectral mixing where we assume that each pixel is basically linearly dependent on each of the land cover class considered. Then, depending on the coefficient, we find out the proportion in that pixel of the land cover class. So that's the story about it. Now, again, subpixel classification. It is used when spatial resolution of image is lower than the size of land cover features of interest or in regions where there is significant mixing between different land cover types. So it's very straightforward now. Now let's move to the next question. Taxonomically correct definition of class information organized according to logical criteria is called A classification scheme, B hierarchical scheme, C exhaustive scheme, or D spatial scheme. This we all know, it is the classification scheme basically. And classification scheme in general is the organizing or grouping objects or data into categories or classes based on their attributes. That is what a classification scheme is all about. Next, MODIS LULC, land use land cover. A product is generated at an interval of 1 year, 5 year, monthly, once in 6 years. It's actually 6 months. It's actually 1 year. It's an annual product, and it is produced under several schemes also. Like in one of the schemes, they only give you the nominant plant functional types, uh, like whether the C3 grass is prominent in one place, or C4 grass is prominent in one place, or it's a forested land pixel, and something like that. But let me just introduce the most important land cover classification scheme for us uh, eco hydrologists. That is something known as the IGBP classification. That is also produced by Modis. Uh, that is produced by several other products also, by the way, because it's the most famous land cover classification type. So IGBP stands for International Geosphere Biosphere Program. Okay, and it basically has 17 land cover classes. Land cover types. Those 17s are: number one, evergreen needle-leaf forest. Then let it be ENF. Then evergreen broadleaf forest. Then deciduous needle-leaf forest. Then deciduous broadleaf forest. Then mixed forest, in which I mean, a dominant proportion of both evergreen and dominant classes may be there, or evergreen needle-leaf and evergreen forest are there. So that is termed as the mixed forest. This modest land cover product, according to the year 2010, gives us, I mean, states that around 10 percentage of the total land cover of India is actually forested land. It is very less, and according to different estimates, this land cover percentage across India varies. Uh, for example, the estimate given by the CFRI, Central Forest Research Institute, is around 22 to 24 percentage across India. So you might be wondering, why does the estimate vary so much from 10 percentage given by Modis to 20 to 24 percentage given by the other products? The thing is that this Modis product is available at a spatial resolution of around 500 meters, whereas the other products are at a much I mean, which report a higher forested percentage. They are available at a much finer spatial resolution. So due to it, that percentage of forest varies a lot. Okay. Secondly, the definitions of what a forest exactly is also varies among the scientific community. Some of them consider uh, preserved forest within urbanized localities as forest class. Some of them don't. Uh, so in the former, you may see that the forest percentage is much more, whereas in the latter, you will find that the forest percentage is much less. So anyway, Modis estimates the forest percentage as per its 2010 annual land cover classification to be around uh, 10 percentage across India, whereas the same according to the decadal land use land cover classification of India is around 22 percentage as per its 2005 classification. That is, I believe, at a much finer spatial resolution of 100 meters, and it is built out of cartosat programs, ISRO based programs. uh, so that's the thing. Now these are the first five land cover classes, which are all based on forested classes. Now then, sixth one is the closed shrublands. Seventh one, open shrublands. Eighth one is woody savannas, where the wood percentage is more. Ninth is savanna. 10th, grasslands. Grasslands are also around 10 percentage as per the modest land cover class of the year 2010, around 10 percentage. Now different products show very different percentage fraction of grasslands also. Like the decadal land use land cover showed the grassland percentage across India to be around 5 percentage, if I'm not wrong. The value is in single digits. Okay. Then the permanent wetlands, which is very important in ecologically speaking. 12th one is the cropland land cover class. Now India is an agriculture dominated country, and the croplands class itself constitutes of around 59 percentage of the total land area according to the modest 2010 classification. This according to the decadal land use land cover classification, the croplands area is around 52 or 51 percentage of the total land area of India, so it's massive. It's in itself it actually exceeds the 50 percentage marks, I mean halfway mark, so it's that massive. India's reliance on agriculture is huge, and I mean it goes without saying that the cropland proportion has to be the largest one. Then 13 is the urban and built up land. Then comes 14. 14 is uh, composite natural vegetation, I mean cropland and natural vegetation mosaic. Okay. Then 15 is the snow and ice. You will find it a lot as you, I mean, move towards the higher altitude areas like that of the Himalayas. The 16th land cover type is the barren land cover type where there is not enough vegetation, and the 17th one is that of the water bodies. So these are the 17 land cover classes as per the IGBP classification given by Modis. Modis gives, I mean, gives his products according to different other classification approaches also, by the way. But IGBP is the one which many hydrologists use in their research. So I thought of discussing this to you. Now, vegetation index based models for ETR, they are actually empirical model. And I will be showing one of the example towards the end of this today's weekly live session. Okay, so the actual evapotranspiration, let us say ETA, is ET naught, the reference evapotranspiration, ET naught times vegetation index to the power some eta. Let it be any vegetation index. It may be NDVI, it may be the soil adjusted vegetation index, it may be the enhanced vegetation index. So it is in some way empirically linked, and this eta term is found out empirically basically. Eta is determined by a relationship between transpiration. Why transpiration? Because if you segregate evapotranspiration into its two components, the bare soil evaporation and the transpiration is the one which is controlled by vegetation, hence it has to deal with the vegetation index, transpiration, and the VI, that is the vegetation index used. Okay, so the vegetation index may be, let us say, NDVI, which you all know is reflectance between difference between the NIR band and the red band to the sum of them, or the soil adjusted vegetation index. Sorry. Okay, so this is basically rho NIR, the reflectance. Rho means the reflectance, okay, minus rho red band times some correction 1 plus L by rho NIR plus rho red plus L. So this is because the proportion of soil may vary within the pixel, or also because NDVI gets saturated at higher value. So some sort of corrections are given. We already discussed this probably in weekly live session 5 and 6. Then there is EVI, Enhanced Vegetation Index. It is G. G is some constant again. Rho NIR minus rho red by rho NIR plus C1 times rho red plus C2 times rho blue plus L. That is the story about the EVI, the Enhanced Vegetation Index. Okay. Now, heat transfer from surface to atmosphere is by, it is convection, it's straightforward. There are three fundamental processes of heat transfer. They are conduction, radiation, and convection. So, convection is the transfer of heat by the mass movement of a fluid such as water and air. Please give me 1 minute. I will be back soon. Hello. So we are done with explanation of convection. There is another fundamental heat transfer process known as the conduction. Conduction is transfer of heat from a warmer object to a colder object through molecular interaction. So there is a molecule to molecule interaction. And radiation we know very well. So far we have finished many weekly live sessions discussing radiation. It happens by the propagation of the electromagnetic waves. So due to electromagnetic waves, and of course depends on the wavelength. The energy is h nu or hc by lambda, so it depends of course on the wavelength of electromagnetic wave determines it. Okay, so let's move ahead. to the next question, sixth question for the day. So the sixth question is evapotranspiration can be estimated using the equation. Uh, yeah, so it's very straightforward. Let me show. So the fundamental surface energy balance equation is, we know that evapotranspiration is the mass counterpart of the latent energy heat flux. So the surface energy balance is Rn minus G is equal to H plus Le plus Q. Okay, and all of them are represented by watts per meter square. All of these are energy units. First of all, Rn is the net radiation. Rn is the net radiation, which is positive downward. Okay, Le is the latent heat flux, which is the evapotranspiration counterpart. And it is positive upward. Then H is a sensible heat flux, which is again positive upward. So these two, the sensible heat flux and the latent heat flux, are also known as the turbulent fluxes, surface fluxes. And latent heat flux is the energy required when there is a phase transformation, that is from water to vapor phase, whereas sensible heat flux is only when the temperature changes but the phase remains same. Then G is the soil heat flux, which is positive downward. And Q, which in many cases is not used at all, Q is the residual of the closure of the energy balance. The residual of the closure of energy balance. Let me show what that is. So ideally Rn minus G should be exactly equal to H plus Le. So we plot Rn minus G on y axis or x axis and H plus Le on the x axis or y axis, vice versa also. So ideally the curve should be 1 is to 1. It is the ideal outlook. It should be 1 is to 1, but that does not happen. We see plots here and there and here and there, so it is never 1. So Q is the one which Q is the additional one which you add, so that this becomes a linear formulation. Let us suppose this is r y equal to mx plus c, right? So this would be Q, the intersect will be Q in that case. Okay, so that is the thing. Now let us suppose the Q is 0. Assume Q is 0. This implies the latent heat flux would be what? Rn minus G minus H. Okay, and what is that exactly? That is nothing but part A. So option A is the answer. Now let's look at it. I mean, in further detail. What is this exactly? Let's look at it in further. Uh, let's just magnify what it actually means, or how it is actually derived. So there is something called the Bowen ratio, or let us denote it as beta, is Cp by lambda times the gradient of surface temperature, surface of by the gradient of specific humidity. Cp is the specific heat of air for constant pressure. For constant pressure, lambda is the latent heat flux. Latent heat of vaporization, of water. Q is the specific humidity. Delta T is the gradient of the air temperature at the surface. Gradient of air temperatures at the two levels of measurements. Okay, so let us suppose we have fixed it at two levels. One is Z1 and the other one is Z2. This is T1, this is T2. So delta T would be T1 minus T2, the gradient. Similarly, at the same two levels, Z1 and Z2, we may also install some specific humidity measurements. They will be Q1 and Q2. So delta Q would be Q1 minus Q2. So delta Q is the gradient of specific humidity at the two levels of measurements. Okay. Uh, Now, the sensible heat flux is represented in terms of the Bowen ratio as uh, H equal to beta by 1 plus beta times Rn minus G. That is whatever was on the left hand side of that governing equation, and the latent heat flux would be 1 by beta plus 1 times Rn minus G. So it's that straightforward. Now let's move to the next question. As soil moisture increases, surface reflectance. So in general, with an increase in the soil moisture, we discussed it earlier also, by the way, the surface reflectance decreases. Just straightforward, by the way, so would not dwell a lot of time on it. Next up, generally microwave data is preferable to optical and thermal data for soil moisture estimation. Select the reasons given below. Select all that apply. Okay, so A, the optical data can't be obtained in cloudy conditions. It is very correct, by the way, right? Because you cannot penetrate it because of the cloudy conditions, whereas microwave wavelength can even penetrate cloudy conditions. So A is definitely correct. B is microwave data have better spatial resolution than optical. No, that is not the storyline. C, nighttime data not available for optical. That is also correct, because at the night time you cannot sense uh, a lot of radiation coming towards your sensor, because optical sensors are mostly passive in nature. They rely on the radiation from rely on the solar radiation, so that is also correct. Micro data, free data, that is, I mean, it may be free, but it does not make it better than that of an optical or thermal data. So D is not correct. So A and C are the correct answers for it. Emissivity of dry soil is dash than that of the moist soil in microwave region. Again, it's higher. It's a straightforward theoretical question, so it's higher. Then the brightness temperature depends on a dash, depends all that apply. It depends on A, vegetation. Yes, it does. Depends on surface roughness. Yes, we did discuss that. Depends on soil moisture. Yes. Wind speed, no, because wind speed is not a surface quantity. And atmospheric emission, yes, again. So A, B, C, and E are correct answers for it. So brightness temperature, is basically the temperature which is detected by the sensor based on the radiance concepts. You know that already. So brightness temperature is a measurement of the radiance the microwave radiation traveling upward from the top of the atmosphere to the satellite, from the top of the atmosphere to the satellite, expressed in units of the temperature of an equivalent black body. Okay, so we have already discussed a lot about it. We also solved a few questions uh, when we were into thermal infrared remote sensing concepts. So we know these things already, by the way. So just to wrap up today's class, I would be discussing a bit about the empirical methods of finding the evapotranspiration, which was discussed in one of the questions. So where is that question? Just a second. Yes. So in question number 4, we discussed that vegetation index based models for ET are empirical models. So empirical means that we link some vegetation index empirically, through some numbers done through some experimental approaches to finally find out the actual evapotranspiration. Okay, not the reference or potential evapotranspiration. We are talking about the actual evapotranspiration here. So I will be showing. I just wanted to demonstrate one model to wrap up today's weekly live session, which utilizes an empirical based vegetation index based approach to arrive at the actual evapotranspiration. So yes, the model is known as the metric model. So this metric, all caps, arrives from the acronym stands for mapping evapotranspiration at high resolution using internalized calibration. So M, E, T from the transpiration, R from resolution, I from internalized, and C from calibration. So these, the caps, the capital letters which I am showing, depict the acronym metric. So it is actually developed out of LAI and the soil adjusted vegetation index. So LAI, according to this model, is minus ln 0.69 minus soil adjusted vegetation index by 0.59 by 0.91. So wherever you see some abnormal numbers like 0.69, 0.59, 0.91, these are most likely there. The numbers are most likely present there because of some empirical formulations. Okay. So it uses surface reflectance data because SAVI, SAVI as well as SAVI comes from surface reflectance features itself. We discussed that also in one of the earlier questions discussed today, right? Yes. So soil adjusted radiation index is the difference between the NIR band and red band multiplied by some correction 1 plus L divided by NIR plus red plus some correction L again. Okay, so let's use a surface reflectance features. Okay, so that is a story about the LAI. Now, what about how do we calculate the SAVI? Let me do it in the next one. Next one. Now, according to metric, the calculation of the soil adjusted vegetation index happens like for in case you are using Landsat 7 data, SAVI will be 1 plus L NIR in which is the fourth band minus red which is the third band by L plus NIR which is the fourth band of Landsat 7 plus red band which is the third band. Okay. Now what about Landsat 8? We know that the spectral resolution is different in Landsat 8 from Landsat 7. So the bands may not exactly match that of Landsat 7. So the equation changes a bit. It is NIR which is present in band 5 minus red which is present in band 4 by L plus NIR from band 5 plus red from band 4. Okay, where L is a constant, where L is a constant, L is usually taken as 0.1. Okay, so that is the first step. Now after this we need to find out the surface temperature, and the surface temperature comes out from radiometric concepts only. Surface temperature Ts is K2 by ln epsilon ns, K1 by Rc plus 1. So epsilon something went missing, I hope. Okay. Some problem start, I mean, right, for some reason I don't know why. No idea why we are facing this issue. Text or NPTEL remote sensing. Okay. Fine. So we did discuss till the SAVI. Now the surface temperature. Or Ts is, I mean, we have already derived this also, by the way, so should not be an issue. K2 by ln epsilon nb, K1 by Rc plus 1. So epsilon nb is the narrowband, something known as the narrowband emissivity corresponding to the satellite thermal sensor wavelength band. Rc is the corrected thermal radiance. from the surface and K1 and K2 are constants, and we know that K1 and K2 are given in the USGS Landsat handbook also. Okay, but let me just give some values. K1 is 666.1 and K2 is 1282.7 for Landsat 7. Someone's trying to enter. For Landsat 7, which according to their band numbers of thermal band is band 6. Similarly, K1 is 480.9 and K2 is 1201.1 for Landsat 8, which is according to their band convention of thermal infrared is band 10. We have already discussed its derivation in probably weekly live session 5 or 6. So I will not dwell into that for the time being. We'll take another slide. Now the surface emissivity, which is important for surface emissivity, which is important for the calculation of the actual evapotranspiration. The emissivity in the narrow band is calculated as in the metric model. When there is a vegetated surface, that means NDVI is greater than 0, it would be uh, equal to 0.97 plus 0.0033 LAI. So this is dependent on another vegetation index, that is the leaf area index, and the numbers you see are from empirical formulations. For LAI less than equal to 3 or epsilon NB is equal to 0.98 when LAI is greater than 3. Now, when NDVI is less than 0, that means that the pixel is non-vegetated. What if it's water? Water means that its surface reflectance or the albedo would be abnormally lower. So that albedo epsilon, let us say, is 0.47. The epsilon NB in that case would be 0.99. And if it is snow, snow has abnormally high surface reflectance. We know that very well. So albedo would be, let us say, 0 more than 0.47. So epsilon NB is again taken as 0.99 for that case. Now to come to the actual expression for the evapotranspiration. Uh, to estimate actual evapotranspiration, let me show it as ET suffix A. So LE from the surface energy itself, which we discussed in the previous question, uh, that was, I think, yes, question number 6. LE is Rn minus G minus the sensible heat flux. We know that already. So what about these components? How do we calculate Rn? How do we calculate G? How do we calculate the sensible heat flux H? So to calculate net radiation or Rn, we arrive as Rn equal to downward shortwave radiation minus albedo times downward shortwave incoming radiation, long wave radiation minus RL minus 1 minus epsilon naught times RL again. Yeah, so the first expression is the incoming shortwave radiation which is nothing but the solar radiation in case of passive remote sensing. So this is nothing but the solar radiation. The next part is incoming long wave radiation. Long wave radiation. Then this is the outgoing long wave radiation. Sorry, this is wrongly written. Outgoing long wave radiation. And this is the fraction of incoming radiation, the long coming one, reflected from surface. So alpha here is nothing but the albedo, which is the broadband reflectance. It is dimensionless. We all know. Epsilon is the emissivity, which is the uh, uh, emissivity emissivity, which is again the dimensionless quantity. It's the thermal emissivity. Okay. Now let's just wrap it up. So we now know how to find out the Rn, that is the net radiation. What about the other components? The soil heat, the ground heat flux or the soil heat flux and the sensible heat flux. The soil heat flux G, it is calculated as G by Rn equal to, again empirical formulations, 0.05 plus 0.18 exponential. Exponential means e to the power minus 0.521 LAI. So it's very similar to that extinction characteristics which I discussed early on. LAI is when LAI is greater than 0.5, and it will be 1.80 times the surface temperature, which we found out through some radiometric approaches, minus 273.15 by Rn plus 0.084. It happens when LAI is less than 0.5. So that's the one. Now sensible heat flux, the last component of that jigsaw puzzle to find out the latent heat flux, is found as H equal to the density of the air, that is rho air, times the specific uh, heat at constant pressure, times the gradient of temperature by the aerodynamic resistance. So this is RAH is the aerodynamic resistance to heat transfer. Resistance to heat transfer. The units of this is seconds per meter. And finally, we now know, I mean, through this equation, we would find out the LE, that is latent heat flux. But what about the actual evapotranspiration? How do we come into the instantaneous evapotranspiration through the latent heat flux? Let's see that again. The instantaneous ET, or let me show it as ET instantaneous, is found for each pixel according to metric. Pixel as, so ET instantaneous is 3600. The LE by uh, the vaporization, the latent heat of evaporation, sorry, times density of water. So here lambda is the latent heat of evaporation, or vaporization. The units of this would be joules per kg, by the way. So through this we find out the instantaneous evapotranspiration. How would we find out the daily evapotranspiration, or let us say seasonal evapotranspiration, or the annual evapotranspiration? Uh, in India, because of the phenology as well as the dominant role of seasonality, I mean the climatic seasonality, we see that the evapotranspiration also exhibits a very dominant seasonal behavior. So I'm trying to enter.
चले रही है
Okay,
क्लास
so
भी चले रही है
evapotranspiration also shows a very dominant seasonal behavior in India. Usually, evapotranspiration is constrained by either limitation of energy or a limitation of water. So, if a pixel has less amount of energy, the evapotranspiration would be low. If a pixel has less amount of water, the evapotranspiration would be low. And what do we get out of it? What do we actually mean? I mean, this means that if the evapotranspiration is low, that would mean that the vegetation is under stress. So that's the actual story. Now, latent heat of evapotranspiration is again a very empirical approach, 2.501 minus 0.00236. The surface temperature minus 273.15 times 10 to the power 6 according to this metric approach. Now, we need to find out the reference evapotranspiration. Okay. The reference ET fraction ETRF, which is also in some literature shown as Kc, which is the crop coefficient. So we know very well that the actual evapotranspiration is Kc times the reference evapotranspiration. ETA is equal to Kc times ET naught. So that is very similar. This reference ET fraction is exactly the same thing. So ETR fraction is ET instantaneous, which is the actual evapotranspiration, by the ET reference, and this ET reference comes out from nearby meteorological towers. ET reference is not a function of vegetation; it is only a function of the meteorological conditions. Say the wind speed, say the temperature. That's it. It has nothing to do with vegetation. The vegetation part is only observed in the actual evapotranspiration. Okay, so let me also write it up. ETR is the reference evapotranspiration, and this is obtained from local weather data. Okay, so far we know what is the instantaneous evapotranspiration, and we also know the reference evapotranspiration or the crop coefficient, which is what many literature studies refer it to. Now, what? How to find out the daily ET? Daily ET. So daily ET is nothing but the just multiplied the evapotranspiration fraction, that is the Kc, with that of the reference evapotranspiration over the 24 hours, that is ET 24 over 24 hours is nothing but uh, reference evapotranspiration fraction, multiply it by the evapotranspiration reference evapotranspiration over 24 hours. That's it. Units would be per day. Now, how do we find out the monthly one? Monthly and seasonal evapotranspiration. It's very simple. You just integrate it over that time period. Integrate over the time duration. So through this you know the daily evapotranspiration already. That is in per day. What if you want to know the evapotranspiration over the month of January, let us say? So you can just integrate it, or in very simple terms, you can just sum up the daily evapotranspirations for each day of January. So let us say the evapotranspiration is around 1.5 per day, and if January has 31 days, and January actually has 31 days, so the monthly January evapotranspiration would be 1.5 mm per day times 31. So that would be in mm per month, by the way. The unit would be in mm per month. That is the only thing. Same is the case with seasonal evapotranspiration. So if you want to find out, let us say the evapotranspiration over the monsoon, according to IMD, the Indian Meteorological Departments, the 4 months of monsoon are June, July, August, September. So you just need to integrate it over the 4 months of monsoon. So that's the storyline. So we understood one of the methods which links vegetation indices to the evapotranspiration. We discussed that, and apart from that, we also discussed 10 different questions. Uh, so with this, I think we are done for the day. We will wrap it up now. In the next weekly live session, I will be only discussing the problems, the important problems which I feel would be relevant to the exam uh, for our revision purpose. That's it. Let me stop recording it.